today I came with the simple and whole circuit. Okay, simple and hold circuit, right? Yeah, we can also call the track and hold circuit. This is also called as track and hold circuit, right? So in this, I'm going to explain. I'm taking the one switch here, right? With capacitance, right? Charging capacitance CH. This is the switch. Here I am applying the input supply. Here I am getting the output. Okay. So if I apply the sinusoidal input here like this, so this is the VI. Okay. Sinusoidal input. Okay. Sinusoidal input. Why this is happening? Yeah. Not okay. Let's see for this one. Okay. This is VI with respect to T. If I applied the clock for the switches here, this is the clock. Okay. So if the clock is high, my switch will turn on, right? So when the switch will turn on, so in this duration, the signal will sample at the output side by the using of the switch and capacitor, right? So as we know, so what kind of switches I put there in the sample and hold circuit? So that is the matter actually. Okay. So if I put the NMOS there, right? This is the NMOS. Okay. And this is the PMOS. And one is the transmission gate. So which circuit is suitable for the switches, right? Okay. This is the transmission gate. Okay. As we know, the NMOS is good for zero low value passer, right? So NMOS is good for low value passer. So how it is good for the low value pass? So we can see like this is the NMOS, right? Okay. If I apply input here, okay, and there is the switches, right? So we cannot say this is the source by seeing that this arrow and this is the drain. We never say this is source and this is drain. So okay, if I apply there is the charging capacitance. If the charging capacitance charge up to the VDD, so we can say this is the drain. Okay. So in NMOS, where the higher value applied, so we are defining that one is the drain and lower value is the source, right? If if I applied the gate voltage VG equal to VDD, so my VGS is how much? VG minus VS, right? Equal to VDD minus VDD. That means 0. If I take the VT is equal to 1 volt, so VGS is less than VT. So here the inmost will turn off, right? And whatever the value at the capacitance charge, it will not discharge through the source, right? So current will not flow. Okay. So take the another example of the similar circuit, right? Okay, I'm going to take the another example of that. Okay. If I take the same NMOS, okay, this is the charging capacitance, this is the VI, this is the gate. right? If I apply the Vi is equal to VDD, okay, this is the capacitance. So which is the source and which is the drain? So here this one is the drain, this one is the source, right? So as per the definition of the inmost, right? So here we can say and capacitor is initially discharged, means VCH is zero voltage initially, right? So here the we can say and we are going to apply the VG equal to VDD. Okay. So here VGS is how much? VG minus VS means VDD minus 0 is equal to VDD. So greater than VT. Okay. So my NMOS will start, NMOS will turn on and current will start flow like this, right? So up to what value of charge capacitance can you say to me? Yeah, I'm going to tell you. Okay, just wait. As we know, VGS is on when it will greater or equal to VT, right? Let's assume VDD is equal to 5 volt. Okay, if it will charge up to 4 volt, I'm assuming like it will charge up to 4 volt and VDD is 5 volt. So VGS is how much? 5 minus 4 is equal to 1 volt. It is equal to VT. So it will turn on. Again, it will start charging. Current will start flow. Let's assume it will charge up to 4.1 volt, right? So in this case, how much VGS? 5 minus 4.1. So how much? This is zero point 0.9 less than VT. So the NMOS will turn off, current will stop flowing, right? And what can I say? Capacitor charge up to the 4 volt, but it is not totally charged up to the 5 volt. So this switch will not work there, right? If I take this kind of switch, so it is not good for equal charging of the what we want to charge. Okay, let's see. So it will its graph look like whatever the output, it, uh, uh, whatever the input 5 volts, it is up to the VTT. Like when the VTT reaches, like so it will stop that point, right? Like we cannot define like this. Just wait. This is not a good way to define the how much it will charge. Okay, I'm taking the case of the PMOS PMOS device. Okay, sorry, for PMOS. Okay, okay. If I take the PMOS, okay, in PMOS case, this is the same definition for PMOS also. Higher value, we are defining the source. Let's assume this is the capacitance. It is charged up to the VDD initially. So we can define this is source and this is drain. This is VI. We can apply here. Okay. So if the capacitor is charged up to the VDD and we applied the VG is 0 volt for PMOS. And when the PMOS will on, so when we apply the lower potential at the PMOS, okay, means zero. If you take the case in digital form, 0 and 1, right? So in this case, how much VGS? 0 minus VDD minus VDD. Sorry. So in this case, and VTP, let's assume minus 1 volt. Magnitude VTP is 1 volt, right? So VGS is less than VTP. So PMOS will on, right? So current will start flow from source to drain in PMOS. Got it? This is the definition of the PMOS. Like in NMOS, current will start flow from drain to source. Drain, where how we identify the drain, where the higher voltage applied. Okay. In PMOS, how we can identify which one is source and which one is drain, where the higher voltage is applied, which is source, lower voltage is drain, right? So it start flowing the current and capacitor start discharge through this way, right? If the capacitor, let's assume VDD is 5 volt, okay? So if if it will discharge to the 4 volt VCH and it will go beyond like 3 volt, 2 volt, okay? Let's assume 2 volt. So in that case, what is the VGS? 0 minus 2. How much? Minus 2. Less than VTP in this case. So current will remains flowing through this. If it will reach 1 volt, capacitor voltage VCH 1 volt. So in that case, what is the VGS? Like 0 minus 1 is equal to minus 1 volt. It is equal to VTP. So if it will go beyond like zero point 0.9, so in that case, what is the value? Minus 0.9. It is greater than minus 1. Okay. In that case, so the PMOS will turn off and current will stop flowing and capacitor not discharge below the minus 1 volt. Okay. So here we can say, so PMOS is good for charging, like passing the higher value, but not for discharging. It will discharge up to the VTP, not below the VTP. And NMOS is good for passing the zero value, lower value. NMOS is not good for charging the value. Okay, we can say by the this concept, right? So I already defined those concepts, why we use the PMOS, why we use the NMOS, where we use the PMOS and where we use the NMOS, right? Okay. So I'm just explaining about the, if you want to use the MOS device as a switch, so uh, it will work on the linear region when it is on. Like, see, if MOS as a switch, so in on condition it is in linear region. In off condition, this will in cutoff region, right? MOS, you all know na, metal oxide semiconductor. Okay, okay. So I'm taking the current equation here. By using this, I will explain the how the input is dependent on the, sorry, how the on resistance, like in linear region there is the resistance. See, in linear region, what is the graph of ID? This is the, sorry, okay. This is the ID graph, right? And this is the VDS. So it will look like this. Now, this is the linear region. This is the saturation region. This is the cutoff region, right? So in linear region, what is the slope? 1 by R on. Okay. Let's see. I'm taking the example of current equation. What is the current equation? In saturation region, half mu n COX W by L VGS minus VT whole square. Okay. What is the current equation in linear region? ID equal to mu n QOX W by L VGS minus VT into VDS minus VDS by 2 whole square, like this. Okay, VDS square by 2. Okay. In linear region, VDS is very low value, right? So VDS square will also the low value compared to VDS. So we can neglect this one and assume this will be, approximately 0, right? Okay. So what is the Ron? Ron we can say this is the defined by the 1 by del I dy del VGS. So it will come if you derive this one with respect to VGS. So you will get the 1 by mu n COX W by L VGS minus VT. Okay. So Ron will depends on the 1 by mu n COX W by L VGS minus VT, right? Okay. So I'm going to explain furthermore like what is the gate voltage like VG we can apply the VDD at source VG is VDD, right, for NMOS, and for PMOS it's a zero voltage. For VS we are going to apply, let's assume there is a switch, NMOS switch. Okay. For sample and whole circuit I'm taking the switch as a NMOS circuit. Okay. NMOS is a switch circuit. Okay. So Vn, right? So let's put this value in the Ron. Okay. Okay. So what kind of equation we get? Like Vg minus Vn, so Vt, like this. Okay. I'm going to further explain like if we increase the Vn, okay, so this denominator part will decrease. Got it? What I'm trying to say. If you increase the Vn, so definitely this is the minus Vg minus Vn. If we increase the Vn, the overall denominator part will decrease. So numerator part will increase. Got it? If you increase the Vn, Ron will increase. Okay. So we can say what kind of graph we get from here. If I take the Ron with respect to Vn graph, okay. So what kind of graph we get? Just okay. So if you increase the vein, iron will increase. So this kind of graph will get. Okay. Okay. And for if you take the case of the PMOS, so this will happen in similar. So what kind of graph we will get in the PMOS if we take the PMOS as a switch. So this is the just opposite of the NMOS, right? If you increase the gain, Ron will decrease. This is for PMOS switches, and this is for NMOS switches. I mentioned there you can get from uh, those equation from Ron equation for NMOS, Ron equation for PMOS. If you derive the Ron equation for PMOS, you will get this kind of graph, right? If you analyze the Ron for NMOS, you will get this kind of graph. Okay. So I'm further going to design the transmission gate. What the Ron will change with Vin if I take the transmission gate. Okay. Okay. So I'm taking the transmission gate here. Okay. Okay. See if I put the 5, this will fiber. Okay. So if I apply V input here and make the capacitance, add the capacitance here, CH. Okay. So what the circuit will come by this? So it will look like this is this kind of circuit we will get. If you just uh, consider about the with respect to Ron. Okay. So what kind of graph we will get from here? So I'm going to draw. So just follow the carefully. Otherwise, you will get confused. So, what kind of switches you are going to take and how it will behave. So, see, we are going to make the switches, yeah, resistance which is independent of Vin. Okay, why independent of Vin? If the supply is vary, like there is a noise come in the supply and there is some boost and bump, like due to sudden the supply is changing, so it will affect your resistance, Aron resistance. So it will definitely affect your switches. So you will not get the exact signal you want to sample that signal. So this will you will get the some disrupted signal at the output side. And in real world, we don't want the disruptive signal. Like if you are watching the movie, if you are watching the news, if you are listening the song, do you want to any disrupting uh, any unwanted noise come? And so it what kind why you pay so much money for that device? You want to get the smooth signal, you want to get the smooth video, you want to get the smooth song. So that's why we are going to design the circuit which is independent of the supply. That's why if the supply is vary due to certain region, so our device will not um affect by that. Okay, or affect by the signal. So what kind of Aaron will get from here? Like see, for PMOS, this is kind of the graph we got now, and this is for PMOS. Okay, and for NMOS we got this kind of graph, right? And if we use the sorry for if we use the transmission gate, we get the this kind of graph. Like okay, so it is little bit better than PMOS and NMOS. It is quite better than little bit. No, we can't say little bit, but it is quite better than NMOS and PMOS. This is for the transmission gate, but it is not a smooth. But we want to a smooth signal. We want to a smooth sample the signal at the output side. So what we are going to change? Okay, let's just wait for a second. Okay, okay. So I'm going to explain that circuit which we want to add on the sample and hold circuit. So which will uh, reduce the effect of the input and we get the exact signal as we want. Okay, so we are going to design that kind of circuit. Okay, just wait. So this is the NMOS switches, right? This is the capacitance, charging capacitance. Here we are going to apply the input, right? Okay, so let's assume. Okay, just a bit. This is the Vin, right? If we apply the Vin some value, so it will come into the R1 part, R1 resistance as I define mu n Cox W by L Vg minus Vin minus Vt. You all know na? Okay. So if high at gate voltage like Vg, VDD if we apply, so we get this kind of input dependent Auron resistance. Okay. If I add the Vin here, so this is the source, this is the gate. So if I take the VGS, so VG is VDD plus Vin and source is Vin. So it will get cancel out only left with the VDD. It will independent of the Vin. So how we can get the Vin here, right? How we can get? So I'm going to add the circuit through which can get the Vin at the gate side from there. So okay, if I add the capacitance battery here, first I'm explaining the battery or which is the value of VDD. So it will come. Let's remove that part so we will get clear. Vin plus VDD. Right now? Okay. So we can replace the battery by the capacitor. Okay. Capacitor is the chargeable device, so we can charge up to the VDD, right? Okay. So how we get the VDD at the capacitor charge? In capacitor. So there is the again we add the switch which will charge through the some input. Okay. So I'm going to design that kind of circuit here. Okay. So just taking the NMOS switch. Yeah. If you go for the higher study, you will get the this sample and hold circuit topic in the mixed signal. If you go for the higher study like MTech, so there is the course of mixed signal you will get from this topic from mixed signal subject. Okay, okay. This is the VN. Okay, so I'm adding a capacitance here. Okay, there is the switch, right? And there is the another switch. I will explain one by one why we are adding the switch and which switch is which kind of switch like NMOS, PMOS, transmission gate. I will explain. Just wait for a second. Okay. Why I am adding the switch and which switch will VDD, sorry, NMOS या PMOS. Okay. And what is the uh, this kind of switch? What is we can say? Like this circuit is called as a bootstrap switch, like voltage doubler switch. We can say the voltage doubler switch. How we can say? I am going to explain. Okay. Okay. Like see, uh, I mentioned the name of the every switch. This is the phi 1. This is the same phi 1, and this is the phi 2 switch, and this is the phi 2 switch, and this is the phi 2. Just this is phi 2 switch. And I also mention the name of the switch number. Okay, this is the S1, and this is the S2, this is the S3, this is the S4. Okay, and this is the S5. Okay, so uh, let's assume if the Vin is start charging this capacitance, so it will follow this path to charge. Okay, once it will charge, though, so we can switch off the this switches and this switches fast phi 2, and it will start discharging the capacitance through this path. Got it? Okay, okay, okay. So this is the VN here, and this is the boot. We can say this is the boot strap switches. This kind of circuit, yeah, this kind of switches we are defining the bootstrap switches, yeah, voltage doubler, right? Okay, this is a sampling switch. Okay, at the end, So what kind of equivalent circuit we will get? Okay. Once the capacitor will charge, so what is the sampling circuit actually look like at the end? Okay. This will look like, I'm going to draw. Okay. Just take a look here. Okay. Yeah. This is plus minus VDD. Once it will charge up to VDD, this is the equivalent circuit of sampling phi, right? During the charge, during the charging, during the hold of the phi, like during the charging of the capacitor up to the VDD, so the circuit looks like, okay, this is the VDD, and this is the circuit switching sampling circuit. Okay, this is the VIN, and this is the, the circuit will look like this one. Okay, this is hold on position, hold the phi. Okay, so I'm going to ask you which switches is NMOS and which switches is PMOS. Okay, can you guess and tell me which is NMOS and which is PMOS? Okay, I'm going to ask. S1 switches is which one? Okay, as I explain you, we are going to use in future circuit transmission gate. Okay, transmission gate is the circuit where we apply the in low voltage या high voltage, it will pass both of the value, right? So at the switch S1, which circuit is preferable to add here? Because Vin is, we don't know what kind of Vin we get, like either is 0, yeah, 1. So we can put here S1 is the transmission gate. Okay. So S2 is the, can you think and tell me the what kind of switches we add at the S2? See, at the point this will come Vin plus VDD, right? This is VDD and whatever. We don't know actually. So PMOS is good for charging the uh, capacitor, passing the higher value. So we can use S2 as a PMOS device. S2 switches as a PMOS device, right? Let's come for the S4. So for S4, S4 is the path where we going to discharge the capacitance. Means it help to flow the current. Means which device is good for discharging the value like NMOS. So we put the N S4 switch as a NMOS, and same for the S5, which is also discharging. So S5 is NMOS. Let's come for S3. What kind of S3 we can put? Okay, like the input value Vin is, we can't say like it is 0 or 1. It will either 1 or 0. Okay, here we are going to get a value of the Vn plus VDD. So if so someone say the PMOS we can use, but not. If you use the PMOS, so there is PMOS will create some problem because it is good for charging, it is good for passing the high value, but it is not good for the discharging. Definitely it will create the problem. So by lots of research, so we get the S3 is a NMOS devices. How NMOS devices? So if I add the NMOS devices as S3, so they are definitely need at the gate point there is some supply. So what kind of supply we will get to turn on the device and charge the VDD of that capacitors? Let's think on that. I'm going to explain of the S3. Like okay, first I'm going to design that circuit so you will get clear. Okay, okay, so take a look on that. Okay, 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 okay. I'm going to explain what kind of switches we are going to add here. So first I remove all the part and I'm going to add the those circuit what I explained earlier. Okay, let's take a look on that. Here we can use the transmission gate. Okay, right. This is the if I take the phi 2, no, and this one is the phi 1, no? So this one is the phi 1 bar. This is NMOS, so this is PMOS. Okay, there is the capacitance, right? There is the PMOS devices, right? Okay, this is the NMOS devices. Okay, this is the ground. Okay, this all are phi 1, phi 1. Okay, this is the NMOS devices. Okay, VI apply here, some other VI for charging this capacitance. This is phi 2. Okay, okay, same thing for here. This is the NMOS. This is the ground, phi 2. The overall circuit look like this one. This is the VIN where we are going to apply the input voltage. This is the V out. Okay, this is the final circuit for the sample and hold circuit. This all part is the bootstrap switches, yeah, voltage doubler switches. So it is used for the developing the VIN plus VDD voltage at the gate. Okay, so for this in MOS, here I need the some supply because here we get the value. What kind of value we will get? Vin plus VDD. Okay. So if if this will Vin plus VDD, so this is drain, right? This is source. If VI is VDD, if VDD applied at the gate side, so VGS is 0. So that time it is less than VT, so it will turn off. So how the capacitance will charge to the VIN, sorry, VDD. Okay. So for that, supply the at the gate point of the S3 switches, we use the one another circuit uh, which will make the gate voltage up to the 2 VDD. So in that case, VGS is 2 VDD minus VDD is equal to VDD, which is greater than VT. So then the current will start flow and charge the capacitance up to the VDD. Got it? So one of the scientists name is the Naka Gonage charge pump. The circuit name based on the scientist name. Okay, so I'm going to draw that circuit. Okay, This is the Nakagone charge pump circuit, which is going to use at the for the switch theory. Okay, so the circuit look like this one. This is the inverter. Okay, this is the switch. Okay, this is the capacitance, and this is the where we get the value V I plus VDD, and this side 5R plus VDD. Okay, this is the VDD. Okay, so can you anyone tell to me like the V switch we are going to use at both side? Anyone guesses? Okay, okay, I'm going to tell you. We can replace this circuit by the NMOS, right? So how it will charge up to 2 VDD? Let's take a look. Okay, I'm going to explain you. Okay, okay, just wait. Okay. So I'm going to design the NMOS here. Okay, and NMOS here. This one is connected through the this point. This one is connected through the this point. This is VDD. Okay, and this is phi. This is 5R, right? Okay, okay. Let's take a look on this circuit. Okay, just a bit. How it will charge up to the 2 VDD, right? Okay. If this point, if if I take phi is 0, so 5R will 1, right? Okay. If phi is 0, this is 0. Okay. So this will turn off. Okay. If this one is 1, 5R is, this will 1. 1 means VDD. This will VDD. Okay. It will turn on. How much it will charge up to the, this is NMOS na, so VDD minus VT, right? Okay. If phi is 1, 5R is 0. Sorry, 5R is 0. If 5 is 1 means VDD. Previously it is VDD minus VT. So how much here? 2 VDD minus VT. Okay. So it will turn on this device. So it will charge up to the, previously it was VDD, right? So it will charge up to the VDD. How we can say VDD? It will charge up to the VDD because at the gate we are getting 2 VDD minus VT and source VDD. So how much this one? VDD minus VT. So VGS is VDD minus VT. So it will charge up to the VDD. Okay, got it? So it will comes to VDD, right? So 2 VDD will come at the switch 3 here. So it will properly work for this charging for charging the switches. Okay, sorry, charging the capacitance. So the Nakagone charge pump circuit is used for the switch theory. So for designing the smaller switch, like a what kind of switches? This kind of sample and hold circuit switches. sorry, sample and hold circuit, we are getting that kind of big circuit. Okay, this one is the bootstrap switch. For switch 3, again we need the Nakagone charge pump circuit. So this is the overall about the sample and hold circuit. If you want to more concept on the sample and hold circuit and integrator and amplifier, two stage, gap reference, yeah, RC circuits, which will work for the your interview, which will work for your the getting the job in the analog design. So please connect with my channel. So I will further add more circuit of the analog. Like I will teach you the BGR from basics, how we are design the BGR, how we find the getting the V reference equal to 1.2 volt, which is temperature independent. I will explain you for you uh, ADC part also, and a small like a amplifier, common source, common gate, common drain, some RC circuit which will help you in interview. Thanks for joining my channel, and we will see you with another circuit in the next video. Okay.